Still seeing a decent amount of confusion about vector decomposition. So, in particular, I think that sometimes examples get you into the habit of thinking that certain components are always associated with, say, the cosine, and other components are always associated with the sine. And that's not the case. And I think that'll make more sense if you see where these equations come from in the first place. So, when we're talking about a vector has both a magnitude and a direction. So the magnitude is the length of the vector that I just drew, and then the arrow is the direction it's pointed. So I could, in theory, have exactly the same length, i.e. the same magnitude, but if it was pointed in another direction, that's a different vector, okay? Because it might have the same length, but it's now oriented in a different direction. So vectors have both magnitude and direction. So let's go back. Let's have a vector pointed up and to the right. If you want to think about like a cardinal coordinate system like northeast, southwest, this would be, so if we had north, east, south, and west, this would be pointing in the northeast direction. Part of it would be pointing to the east, and part of it would be pointing to the north. Now, if you want to think about it with your mathematical XY coordinate system, so in other words, if you had a coordinate system where horizontal was X and vertical was Y, then you could think of that vector as having both some component in the X direction and some component in Y direction. And that's the idea, is that these vectors, which are two-dimensional mathematical representations, can be broken down into how much of that vector is oriented in each of the two dimensions that makes it up. So in other words, that vector pointing northeast, I can figure out how much of it is pointing east, and I can also figure out how much of it is pointing north. And so we call that the east component or the north component. But if we wanted to use the traditional mathematical X and Y coordinate system, we would say that the horizontal component is the X component and the vertical component is the Y component. Another way you can think about it is that you have a horizontal component and a vertical component, where you can think of this vertical component as the rise, and you can think of the horizontal component as the run. So there's rise and there's run, and together they make the composite vector. So I want to explain now how we can break a vector down in its components using trigonometry. So let's take a vector, let's orient it up and to the right again. And we are going to ask ourselves, okay, well, how much run is there? In other words, if I'm going to call this vector V, all right, then this component would be the X component of V, all right? And then there's also a run, the upward motion. And so we're going to call this the Y component of V, all right? So the X component is the run, the Y component is the rise. And so how do we break this down? Well, oftentimes you'll be given a problem where there's a vector and you're going to be given some angle. And here's the thing, depending on what the angle that you're given is, you might be using sine, you might be using cosine, you could be even using tangent, okay? Don't get into the habit, for example, of thinking anytime you're talking the X component, it must be the cosine. That's just not the case. It depends how the problem is set up and what angle you're given. So that being said, an introductory way of explaining vector decomposition is they do often give this angle right here. We'll call it theta, okay? And so how do they get the whole cosine stuff and the sine stuff? So this comes down to trigonometry, all right? In trigonometry, when you have a right triangle and so this little square in the corner tells you that's the 90-degree part, all right? When you have a right triangle, you have a hypotenuse, okay? The hypotenuse is the longest leg of the right triangle. And then the two legs that form the 90-degree angle are going to be either the opposite or adjacent side. Now that is relative to what angle you pick, okay? So if this was my angle right here, theta, the opposite side is you go all the way across from the angle. So this would be the opposite side, okay? But that being said, if my angle was instead here, let's call that angle phi, then the opposite side for that would be here, okay? So opposite or adjacent depends on what angle you're talking about. So let me get rid of that. And we'll just focus on one angle again. All right, so let's draw the right triangle again. And you have 90 degrees. And let's call this right here theta. All right, so that means that this is the hypotenuse. You have to go all the way to the opposite side. So this is the opposite side. This is the adjacent side. If I had a right triangle and this was my angle instead, well, now to find the opposite side, you have to go all the way across. So this would be the opposite side. This would be the adjacent side. In both cases, the hypotenuse remains the same. Okay, the hypotenuse is going to be opposite of the 90-degree angle. Okay, here's the key. And so when you have a vector, you can think of that vector as the hypotenuse. And then the horizontal component and vertical component, i.e. the x component and the y component, they can be thought of as either the opposite or adjacent sides. Now that depends on what angle you're focusing on, all right? So if we go back to the original example in the bottom left here, do you see where the theta is? So if we want to identify what's opposite of that theta, we have to go all the way across. And so the opposite side is going to be over here. The adjacent side is going to be here. And of course, you have the hypotenuse again. Remember, the hypotenuse is going to be the longest leg. It's going to be opposite the 90-degree angle. So we usually use our vector that we're given in the problem as the hypotenuse and then break it down into its horizontal and vertical components. All right, so here's the key. This is an acronym that is very helpful to remember. This is the way that I learned it. It's called SOHCAHTOA. So S-O-H, that's the so. C-A-H, that's the ka. And TOA, T-O-A. SOHCAHTOA. When you're remembering stuff, it makes it even easier to remember if you try to associate it with something else when you're encoding it in your brain. So I'm really into snowboarding, for example. And so I've always like pictured the fictitious Mount SOHCAHTOA, because I picture like you would go to Mount SOHCAHTOA and you would go snowboarding. So that's what helps me kind of memorize SOHCAHTOA. But of course, you can write this down on your notes, and you can even use your notes on the test. And so SOHCAHTOA tells you the trigonometry of how the different opposite, adjacent, hypotenuse sides are related to the sine, cosine, and tangent angles. And so SOHCAHTOA stands for the sine of theta equals opposite over hypotenuse. The cosine of theta equals adjacent over hypotenuse. You see how we're using the letters in the acronym here? All right. And the tangent of theta equals opposite over adjacent. So let's go back to the bottom left. You see the angle theta is in the bottom left there, that black angle theta you see there, okay? So that's going to be the main angle in which we're going to determine the opposite and adjacent sides. And so based on the position of that theta, you're going to have opposite be the vertical component and adjacent be the horizontal component. So invoking SOHCAHTOA, I can say that the cosine theta equals the adjacent over the hypotenuse. That's the ka in SOHCAHTOA. Well, I know that the adjacent is going to be the horizontal component. The hypotenuse is the total resultant vector. And I'm going to put these little bars on the side because what we're going to do is we're going to just look at the magnitudes of those vectors. And that's the actual length of the right triangles that we're drawing. And so I can rewrite this. If I multiply both sides by the magnitude of the whole vector, then I have the magnitude of the whole vector multiplied by cosine theta is equal to the magnitude of the horizontal component, i.e. the x component. You see that? That's where the cosine comes from, all right? And when you have the angle defined as I have it there, yes, the horizontal component is the cosine, okay? And so you simply take the magnitude of the whole vector, multiply it by the cosine of the angle, and that gives you how much of it goes in the next direction. That gives you how much run there is, okay? If you want to go with the cardinal coordinate system and it's pointing northeast, this would tell you how much of the vector is going east. Now, when you're dealing with the vertical component, instead, I'm going to use sine theta. And with SOHCAHTOA, that's going to be opposite over hypotenuse, okay? And so that's going to be the y component over the vector. And so that's going to give me the magnitude of the vector multiplied by sine theta equals the vertical component, okay? And that's probably why people sometimes think, oh, well, if it's vertical, it's always sine. But see, this is not necessarily the case. So let's say, for example, that instead of being given the angle you see in the bottom left, let's say that instead you're given this angle right here, and we'll call that phi, all right? So now based on phi, all right, you have this side is opposite of phi, and this side is adjacent to phi. So look now, cosine phi, that's going to equal the adjacent over the hypotenuse. But you see now the adjacent side is not horizontal. Now it's the magnitude of the rise. It's the magnitude of the vertical component. And that's by the hypotenuse. And the hypotenuse remains the same. And so if I multiply both sides by the magnitude of the whole vector, I get v cosine phi equals the magnitude of the vertical. So do you see that? If I wanted vertical when I was given phi, which is in the upper right, as opposed to the black theta you see in the lower left, if instead it's the orange phi in the upper right, then the vertical component is going to involve a cosine term, not a sine term. So don't get into the habit of thinking whenever it's vertical, whenever you see an x, that you're going to use cosine, and whenever you see, whenever you see horizontal and you see an x, you think it's cosine, and whenever you see vertical and you see y, you think it's sine. That's not necessarily the case. You have to think, what angle are we talking about here? Once you know what angle you're talking about here, you can take any two-dimensional vector and you can think of it as a right triangle. The vector itself will be the hypotenuse, and you can break it down into opposite and adjacent sides, where the opposite and adjacent sides are predicated on what your angle is. So that's a little bit about vector decomposition. I encourage you to use SOHCAHTOA or whatever acronym might work for you, so that if you ever get stuck, you can just work through it, just like I did. You can draw the triangle and break it down into its respective sides, and then you can use SOHCAHTOA to write combinations of opposite sides, adjacent sides, hypotenuses, whether you're using sines, cosines, or tangents.